Hi, in this video we are going to see the definition of the Fourier transform of a signal and see some examples of the calculation of the Fourier transform. First, let us see what we mean by the Fourier transform of a signal. So let x of t be a signal. In fact, the function x is from the interval minus infinity to plus infinity into the set of complex numbers. So we have complex valued functions of a real parameter or real variable taking values in the interval from minus infinity to plus infinity. In other words, the entire real axis. Okay, therefore, now if we compare this signal with the signals we have studied in the context of Fourier series, in Fourier series we have periodic signals, but here the signal does not have such a property. It can be aperiodic and it is defined for all values of t between minus infinity and plus infinity. So the Fourier transform of x of t is defined as, we are going to show this by the symbol x of omega, capital X of omega, equal to the integral from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t. Okay, so capital X of omega is called the Fourier transform of x of t. Here omega is again representing the angular frequency in the context of signal theory. Therefore, we have this definition. Now, we have to pay attention to a certain point. I'm going to write down the following as well. Now, this integral, as you see, is an improper integral from minus infinity up to plus infinity. Therefore, we have again the issues of convergence of the integral. So, we have to say that this is the Fourier transform provided that the integral exists. That is, the integral converges. Okay. So the Fourier transform of x of t is given by this integral provided that the integral exists. Now, before we see some examples of the calculation of the Fourier transform, let us see how we interpret this result. What do we mean by this integral? Now, so let us continue with this discussion, interpretation of the Fourier transform. Now the Fourier transform in terms of this integral expression is closely related to the definition of inner product. Now remember the definition of inner product of two vectors in Rn. That means the n-dimensional vectors of ordered n-tuples of real numbers. So x is, for instance, the vector alpha 1, alpha 2 up to alpha n, and y is the vector beta 1, beta 2 up to beta n. Then the inner product of x and y is simply I from 1 to n alpha I, beta I, the product of the corresponding entries, all added from 1 to n. Now in Cn, that means if the vectors are now complex valued, the inner product is different. We have conjugation in the second argument. In Cn, let x be again the vector alpha 1 up to alpha n, and y be beta 1 up to beta n. Then in the inner product, we have this difference from Rn, that we have a conjugation in the second argument. Alpha I, beta I, complex conjugate. Okay. Now why do we have this conjugate? Because if x is equal to y in Rn, that means alpha i's are equal to beta i's. So we have here sum of alpha I square, because beta I is equal to alpha I square. And that is, of course, a non-negative quantity, because we have the summation of squares. Now in Cn, again, when x is equal to y, or the entries are equal to each other pairwise, we require this to be real valued and non-negative. So if beta I is equal to alpha I, then alpha I conjugate, we will have alpha I modulus squared, which is a non-negative quantity. And we have the summation of these non-negative terms, and we have a real valued non-negative result. Now, the inner product definition can be extended to functions. For example, in our space of functions defined in the beginning of our definition of the Fourier transform, we have functions defined over the interval from minus infinity to plus infinity mapped to C. So for instance, let us denote this by the symbol V, because this is in fact a vector space, but at the moment we don't really need the definition of the vector space concept. So let V be the set of functions x mapping the interval minus infinity to plus infinity to C. So we have, okay, let me write this in more complete form. We have the set of functions such that these functions are mapping the interval minus infinity to plus infinity to complex numbers, and for any x1 and x2 in V, we have the inner product of x1 and x2 as the integral now from minus infinity to plus infinity, x1 of t, x2 of t conjugate integrated with respect to t. Of course, here we have some technical details, such as the existence of this integral, because it's an improper integral, therefore we have the convergence issues. Of course, provided that this integral exists. We have the definition of the inner product. So, the Fourier transform can be interpreted as the inner product of x of t and the complex exponential e to j omega t. So x of omega can be interpreted as the inner product of x of t and the complex exponential function e to j omega t. So x of omega is x of t e to j omega t, the inner product of these two functions. Okay, now what about the meaning of the inner product? In fact, inner product is a measure of how much one of the vectors is contained in the other. For instance, in Rn or in Cn, it is very easy to see what we mean by this interpretation of the inner product. If, for instance, x, the inner product of x and y is equal to 0, this means that x and y are orthogonal vectors, and this means that x has no component or 0 component along y, or similarly y has 0 component along x. So, in terms of functions now, the inner product of two functions is a measure of how much one of the functions is contained in the other. Now, in signal theory, remember that the complex exponential function acts as the building block. We are trying to express signals in terms of a superposition of complex exponential signals. So the Fourier transform means, in fact, for any signal x of t, the Fourier transform of x of t evaluated at a particular omega frequency omega means, in fact, how much e to j omega t is contained in x of omega, x of t, sorry. So it's a measure of how much e to j omega t is contained in x of t. Okay, so let us now see some examples by keeping this interpretation in mind. Okay, so x of omega, the Fourier transform of x of t, which is defined as the integral from minus infinity to plus infinity x of t e to minus j omega t integrated with respect to t, is a measure of, in fact, I'm going to write this down in quotations, how much e to j omega t is contained in, okay, again, let us write this in quotations because these are rather vague terms, contained in our original signal x of t, because we interpret this as an inner product, provided that, of course, the expression, which is an improper integral, is convergent. It exists. Okay. Now, x of omega is in general complex valued. So x of omega is complex valued. Therefore, it can be written in the following form. X of omega is equal to, it has a real part xr of omega plus j times xi of omega. Okay, xr of omega is real part of x of omega, and xi of omega is the imaginary part of x of omega. Okay. But remember that any complex quantity can be expressed also in polar form. In polar form, x of omega can be expressed as magnitude of x of omega or modulus of x of omega e to j phase of x of omega. So this is magnitude in fact it is the modulus, right, of x of omega, and the exponent in the complex exponential is called the phase of x of omega. Okay, how can we relate the magnitude and the phase to the real and imaginary parts? In fact, the modulus of x of omega is, or magnitude of x of omega is just xr of omega squared plus xi of omega squared, and we have the square root. This is the modulus. And the phase of x of omega is simply tangent inverse xi of omega divided by xr of omega. Because if we look at the complex plane interpretation, so this is the real axis and this is the imaginary axis. So we have here, for a particular omega, of course, xr of omega, and here we have xi of omega. So this point here is x of omega, and the distance of this point on the complex plane to the origin is just the modulus, and this angle is the phase. So this angle is the phase of x of omega, and this length here, the length of this straight line combining the point x of omega to the origin, is just the modulus or magnitude of x of omega. Okay, so after all these definitions, which are quite straightforward, let us see an example. Okay, we start with an important signal, which is the impulse. Remember the definition of the impulse. The impulse signal is a singular signal, which is zero everywhere except t equal to 0, where it is infinite in magnitude. So it has such a singular behavior. And remember, delta of t has the sampling property. When you multiply a signal x of t with delta of t and integrate, you get the value of that signal at t equal to 0. So the signal is sampled by the impulse. So the Fourier integral from minus infinity to plus infinity, the Fourier transform of delta of t is equal to 1, because remember the sampling property of the impulse, we sample e to minus j omega t at t equal to 0. So when the exponent is 0, we have 1. Okay? So this is our x of omega. So in graphical form, the x of omega in this case is real valued. It turns out to be real valued. And it is equal to 1 for all values of omega. Now remember the interpretation of the Fourier transform. The Fourier transform is a measure of how much e to j omega t is contained in the signal, whose Fourier transform is being calculated. Now, in this case, our signal is delta of t. So, e to j omega t for any omega from minus infinity to plus infinity is contained in a delta of t with equal weight, and that weight is equal to 1. Okay? Well, this is an expected result because, especially with respect to the interpretation of the high frequency behavior, the singular signal is handled by means of the Fourier transform at high frequencies. For high frequencies, we see that you may increase the frequency indefinitely, both in the positive sense or negative sense, and all those high frequency components are present in the signal with equal weight. So those high frequency components are in fact essential to represent the singular behavior of the signal, because the signal is zero from minus infinity to a very small non-negative value, then suddenly at t equal to 0 it jumps to infinity, and then again instantaneously it drops back to 0. So this singular behavior is only possible with the inclusion of the high frequency components. And here all frequency components are represented with the same weight. Okay, now let us see another example. Okay, now in this example, x of t is chosen as the exponential signal e to minus alpha t u of t, where u of t is the unit step signal, where u of t is 1 for t greater than 0 and 0 for t less than 0. So only for positive values of t we have a non-zero signal. For negative values it is 0. Alpha is a positive real constant. Okay, this is our assumption. Since alpha is a positive real constant, the exponential function is a decaying exponential. So in graphical form, the graph of x of t is this. This is e to minus alpha t, and it starts from 1 and decays exponentially as t increases. Okay, now x of omega is from minus infinity to plus infinity. X of t e to minus j omega t integrated with respect to t. So this is equal to from minus infinity to plus infinity. X of t is e to minus alpha t u of t e to minus j omega t integrated with respect to t. But we know that u of t is 0 for t less than 0. Therefore, this integral becomes the integral from 0 to infinity e to minus alpha t e to minus j omega t integrated with respect to t. Now we have the product of two exponential terms. Therefore, we can combine them and write this integral as e to minus alpha plus j omega t integrated with respect to t. So this is equal to minus 1 over alpha plus j omega e to minus alpha plus j omega t evaluated at 0 and infinity. Now, as t tends to infinity, as you see, because of this term e to minus alpha t, the term decays to 0 as t tends to infinity. Okay, again, if we look at the components e to minus alpha t, e to j omega t. Now, this function here, e to j omega t, always takes non-zero values and its magnitude is equal to 1. Therefore, it has no effect on the convergence of the integral. The important term in the discussion related to the convergence issue is the exponential term e to minus alpha t. And alpha is positive. It's a positive constant. Therefore, as t tends to infinity, this will decay to 0. So this decays to 0 as t tends to infinity. Okay, therefore, this means that x of omega is equal to, now when we evaluate, so when t tends to infinity, we have 0 contribution. When t is 0, the complex exponential or the exponential function here is just 1, and therefore the result is 1 over alpha plus j omega. Okay? So obviously, x of omega is complex valued. Now, how can we find the real and imaginary parts of x of omega? So we can just apply the following trick. We have 1 over alpha plus j omega. So multiply the denominator and the numerator by the complex conjugate of the denominator. So this becomes alpha over alpha squared plus omega squared minus j omega divided by alpha squared plus omega squared. Okay? So real part of x of omega is alpha divided by alpha squared plus omega squared, and the imaginary part is minus omega divided by alpha squared plus omega squared. So magnitude of x of omega is 1 over alpha squared plus omega squared square root, and phase of x of omega is tangent inverse minus omega divided by alpha. Okay, so if we plot the magnitude as a function of omega, it is it has such a graph. Of course, when omega gets in magnitude larger values, the magnitude will decay to 0. So the value at omega equal to 0 is 1 over alpha. So this is 1 over alpha. This point is 1 over alpha. And now let us look at the phase expression as a function of omega. Phase of x of omega. Now, how can we plot phase of x of omega? Now, when omega tends to plus infinity, we have tangent inverse of minus infinity. So what is the angle whose tangent is minus infinity? It is minus pi over 2. So this is minus pi over 2. Therefore, asymptotically, the value of the phase will tend to minus pi over 2. Now, when omega tends to minus infinity, we have tangent inverse plus infinity, meaning that we are trying to find the angle whose tangent is plus infinity. So it is pi over 2. Pi over 2. So the phase will have such a graph. It will, okay, it passes through 0 because when omega is equal to 0, tangent inverse 0 is 0. So it passes through 0. So this is the phase, the graph of the phase of the Fourier transform of e to minus alpha t u of t. Now again, if we remember the interpretation of the Fourier transform, the Fourier transform is a measure of how much e to j omega t is contained in the specific signal. Here our signal is this decaying exponential e to minus alpha t u of t. So from the phase, from the magnitude graph, we see that lower frequencies will have, in the positive sense and negative sense, lower frequencies will have a larger weight in the representation of the signal, because magnitude of x of omega makes a peak at omega equal to 0 and then decreases for as the frequencies get higher, both in the positive sense or negative sense. But from the graph we see that again all frequency components are present in this signal. Okay, so we are going to continue in the following videos with some other examples related to the Fourier transform, and the interpretation of the Fourier transform will be much more clear by means of such examples. So thanks for watching.